So that's the last talk for this conference, and that's by Franca Hoffmann from Bonn on using continuum limits to understand data clustering and classification. Very interesting. So welcome, and the floor is yours.
Thank you very much. Yeah, it's a great pleasure to have been part of this program, and also to be the last one speaking at this workshop. I think for all of you, it's been probably lots of interesting talks, a full week. And so maybe you're already a bit saturated with information. So now I will talk about something a little bit different. So different in the sense that I think most of the talks that we have seen this week have been looking at supervised learning techniques. And so now I want to focus on unsupervised and semi-supervised learning. So here, either we're looking at data that comes without any labeling information, and we just want to use the distribution and geometry of the data to understand what a good clustering could be. Or we have some labels, however, we have so few labels that supervised learning techniques would not be suitable. And so in that case, you can actually make use, in addition to the labels, you can make use of the distribution of the data itself and use that geometric information. And so that's then where semi-supervised learning techniques are very useful. And for that, I will introduce the graph Laplacian. Maybe there are some people here that are very familiar with the graph Laplacian. Maybe there are others that are not usually working with the graph Laplacian. So I will introduce why this is a useful tool for data analysis. And then for the algorithms using the graph Laplacian, you usually have to make a number of parameter choices. And one question is, of course, how do you choose these parameters in practice? And especially, are there any theoretical insights that can guide us there instead of just using heuristics on different data sets? And so the angle at which I'm coming to this is with a PDE background, since I come from PDE theory myself, and a lot of these formulations or discrete clustering and classification algorithms have continuum analogs, especially when you take the number of data points to infinity and you consider kind of big data limits, and there are several types of limits that you can take. And with some of these limits, you then end up with weighted elliptic operators that appear. And so I will talk about the analysis of these continuum objects, which then also helps us to get insights into the discrete algorithms on the one hand, and on the other hand, it allows us also to construct potentially new algorithms using these continuum objects. So that's what I'm planning to talk about. And everything that I will mention today, you can also find in these two recent papers. And if in case you have attended the LMS workshop in Bath, that was also mentioned at the beginning of the session, then this will probably be very familiar to you. But yes, I hope that it will give a nice sort of introduction and overview to graph Laplacian learning in general. And for those of you who have attended my previous talk, you may have noticed that this is now not anymore a preprint, but in between this paper has just been accepted to appear in ACHA. Okay, so with that, let me get started just with a very brief introduction to graph-based clustering. So let's say we have some data points, usually in some Euclidean space, and this dimension D can be quite high dimensional. And to cluster data points, we want that similar data points end up in the same cluster. So we need some measure of similarity, which we collect in this similarity matrix W. And so given the data points and these similarity measures as an input, we would then like as an output an allocation of each of the data points to one of K clusters. And so spectral clustering in particular usually proceeds with a two-step procedure. So instead of just clustering the points immediately, first there's like a pre-processing step where we embed all the data points into some lower dimensional space So here, the space that we send the points to is of dimension k, which is the number of clusters, which is usually much lower than dimension d that we started off with. And then in the second step, we cluster those embedded points. And so the idea is that we choose this embedding map F in such a way that it makes the clusters more apparent. So in such a way that then a very simple clustering algorithm such as k-means could easily detect the clusters. And so of course the key question then is how to choose this embedding map F. And on the other hand, because you have these two steps, it also makes these spectral clustering procedures more difficult to analyze and really to give guarantees about the behavior of the algorithm. So this is where the graph Laplacian comes in. So the idea here is that you choose this embedding map as a function of the low-lying eigenvectors of the graph Laplacian. And here the graph Laplacian is a discrete operator that is acting on the graph. So you can write it as a matrix and then just identify what the eigenvalues and eigenvectors are. Okay, so let me give you a very quick sort of setup for these graph Laplacian constructions. And here we need to be a bit more precise now about the measure of similarity that we use. So in general, a typical choice is like a kernelized graph Laplacian, where these weights are given in terms of a kernel. So eta here. And you can even go and reweight this kernel again. So you can then divide each of the similarity measures by the degrees of both of the connected nodes to some power. And of course, alpha equal to 0 is kind of a typical choice. You don't reweight, but one question then would be, what effect does this reweighting have on the performance of the algorithm, for example? And then you can calculate the new reweighted degrees as well. And so then the graph Laplacian is just a matrix, which is the degree matrix minus the weight matrix is the unnormalized graph Laplacian. And then you can again reweight or renormalize with powers of the degree matrix. So here you have basically three parameters that come in: the S, the T, and the alpha, that I will comment on later. And so then if you have such a graph, this might be like connectivity stencils for an orange node, which maybe the first one comes from context of PDE theory, right? If you discretize a PDE, then this kind of gives you a very simple graph structure with a stencil like that. Now, if you use, for example, in ITSA, you might get connectivity stencils that for data that look more like this one in the middle. But then you can also localize the kernel, and we will talk about this later on, because if you, for example, consider more and more data points, or even the limit of taking the number of data points to infinity, you would want to rescale your weighting accordingly. And so then you can, decrease it this way, just by rescaling the connectivity radius. And so this little inner product here, I think, gives a good idea as to why graph Laplacians are useful for extracting this cluster information on data. So if I just look at the inner product of some vector u, so u here has the dimension of the number of data points. So basically assigns a scalar to each data point. And then this is just a quadratic form. So this is here the unnormalized graph Laplacian. And in that case, you can see immediately that all the eigenvalues are greater or equal to 0, and the constant vector gives you 0 eigenvalue. But that doesn't give you any information because it's kind of too simple. But now if you had two disconnected clusters, you can just choose different constants on the different disconnected components, and that would also give you 0. And that does tell you where the clusters are. For example, if you then just do a thresholding. And this is still true if you don't have perfectly disconnected components, then the second eigenvalue is not exactly 0, but it's small. And then if you look at the second eigenvector, which is also called the Pfeiler vector for that reason, you could just threshold it and therefore sort of detect where you expect the clusters to be. So that's just kind of some heuristics. And the same argument goes through if you now look at different normalizations and then defining an inner product in such a way that you still keep the symmetry and that you get a quadratic form. And then again, if you have now k disconnected components, then the first k eigenvalues are 0. the k plus first eigenvalue is positive, and the first k eigenvectors, they span the first k sort of identities of the different clusters. If you have a reweighting, then you have to consider v-weighted characteristic functions on the components. So this is why these objects are used a lot for clustering algorithms. And in particular, they're able to detect sort of complicated geometries like these half-moon examples that we saw in the previous talk by Matthias Erhardt as well. Okay, so as I mentioned at the beginning, what I'm interested in is actually continuum limits of these objects. So I would like to go there first and then show you a bit of analysis on the limiting operators, and then come back to what that means for the discrete clustering algorithms. And so this is just a slide to give you an intuitive picture of what is happening in the limit. So now let's say we have data points that are sampled from something. So this could be some complicated density, or it could be something simple, like here I'm taking a density that is a constant on a dumbbell shape. So just the shape by itself, the domain, induces sort of two clusters that should appear here, right? So I can now pick a kernel and then construct a graph Laplacian on top of this and simply plot the values of the second eigenvector, so the feeler vector, and it looks something like this. And now I go back and I sample more points from the same constant density on this dumbbell. And again, I plot the feeler vector. And so you see already that now if I take more and more points, then on the left-hand side, this would just converge to the constant function on the dumbbell. And on the right-hand side, what you get is actually something that looks like an eigenfunction of the Laplace operator solved on a dumbbell. And that's exactly what it is. And so you can prove that this connection, this connection can be made rigorous and has been made rigorous in several different ways. Now, I don't want to go actually into these limits. There has been a lot of work on that, but I want to sort of look at what can you learn from these continuum objects. So now in a more general setting, let's say I have some data points and I assume that they are sampled from some density. Now in practice, of course, you don't know what that density would be, but then you can use kernel density estimates. And yeah, there's a couple of methods of how you can estimate what that rho should be. So for now, I'm just assuming that we have such a function rho available to us. So I can now go and use these points to construct a graph Laplacian. Or instead, I can use this data density rho, and I can write down a weighted elliptic operator. It looks a bit complicated, but basically, it's just a diffusion operator where I have a diffusion coefficient rho to some power q, and then I divide the u by a power of rho, and outside as well I divide. So I have these three parameters here, p, q, and r, and then I have Neumann boundary conditions. Okay, and so the question then is, of course, how do you make this connection rigorous between the graph Laplacian and this continuum operator? And in fact, you can make an exact relationship between the parameters st and alpha that appear in the reweighting and the normalizations of the matrix, and these powers p, q, and r that you see in the continuum formulation. And so here you see that I'm now using as the kernel eta delta, where the delta is basically rescaling. So if I take delta to 0, then you localize the kernel. All right, so for specific choices of normalizations, this has been done rigorously, and in this by Nicolas Garcia Trios and Dejan Slepčev, and then recently we wrote down sort of the heuristic argument of how you can make that connection even for any kind of normalization. Okay, so but as I said, I just want to kind of convince you that there is this connection between this discrete operator and this continuum operator, and then tell you a bit about the properties of the continuum operator. But so one most intuitive, I think, or most simple way of convincing yourself that there is this relationship between these operators is to look at the Dirichlet energy. So the discrete Dirichlet energy would just be the inner product of your vector u with Lu, and you want to reweight it in the good way with the number of data points and then this localization parameter delta. And so this is just, again, the quadratic form that you get. And now you send the number of data points to infinity, and you assume that the data has been sampled from rho. So this, just by the law of large numbers, you get an integral formulation like that. And actually, you could stop here. So there's also a number of clustering algorithms that use these integral operators instead, and their eigenfunctions and eigenvalues. But now, if you wanted to also localize at the same time, the benefit is that, you know, the dependence on the kernel gets all pushed into this multiplicative constant here. So in other words, if I take delta to 0 now, then this difference here approaches a gradient. I get a rho squared term, and then I can rewrite this as an inner product between u and LU, where LU is the operator that I showed you on the previous slide with the parameters 1, 2, and 0. So just by integration by parts. And this constant here just depends on the second moment of eta. And technically also on the first moment, but we just normalize the eta to be 1. Okay. So what we would like to understand is how do these algorithms behave under perturbation? So basically, if you have perfect clusters in your data, then you know exactly what happens. However, if you don't have perfect clusters, which is what happens usually in practice, then it's not so clear. And so what we would like to do is look at tiny perturbations from the perfectly clustered case, and then understand how well the algorithm does in terms of that perturbation. And so in the discrete case, you can do that very simply by just perturbing the weights, get these weak connections. And this is something we did in another paper, also with Bamnat Husseini, Andrew Stewart, and then Jiren, who was a student with us at CALTECH and who's now doing a PhD at MIT. But now on the continuum, the notion of what you mean by perturbing is a little bit different. And so what we consider here is to actually perturb the density itself. So we take a density that has disconnected components. And then, of course, the elliptic operator is only defined on those components, not in between. But now we can perturb this density and have a perturbation rho 0, for example, just a smoothing of that density. And then we look at the perturbed operator, L epsilon, and you can now ask the questions of, you know, how do the eigenvectors and eigenvalues of this operator depend on epsilon? And it turns out that that's not so easy, in fact. And I just want to give you a summary of the results here. And what's really interesting is that by looking at these continuum operators, we have understood something about the behavior also of the discrete operators. At least numerically, we can see that the same behavior persists. So the first eigenvalue is always 0. The second eigenvalue is small, not exactly 0, because we don't have perfect two clusters, but we can say exactly what is the order in epsilon. It's epsilon to the q. And then the interesting part is, of course, the third eigenvalue. So ideally, you would like that your third eigenvalue does not depend on epsilon, so that you have a clear spectral gap there if you're looking at just a two cluster scenario. But that's not always the case. And that depends on how your P, Q, and R are related. And so in the case where you do have a uniform spectral gap, we call that the balance case. And then in the other two cases, we can only show that there's a spectral ratio gap. So in other words, both the second and the third eigenvalue decrease to 0, but the second decreases quicker to 0 than the third. And then we can also look exactly how the eigenfunctions behave in epsilon. So we also have exact estimates here in terms of the order of epsilon, which I just didn't write. But yeah, so we can also show how exactly they're approaching the eigenfunctions of the limiting operator. Okay, and just to mention that for the proofs, we had some very strict assumptions on how exactly this perturbation rho epsilon is constructed. But then we did a couple of numerical experiments just to check if the observed behavior that we saw in terms of the choices of normalizations also manifest in cases where we break those assumptions. And it was interesting to see that indeed that behavior is much more general. So here's, for example, one example of a mixture model that concentrates in the limit just on the sides here on these lines. And also then we can see that if you take balanced normalizations, the third eigenvalue stays bounded away from 0, but the second eigenvalue goes to 0 as you take this parameter. Here it is omega, but it plays the same role as epsilon, goes to 0. And then on the other hand, if you are in the unbalanced case, then the third eigenvalue also decreases, but not as quickly as the second eigenvalue. That's basically the picture to have in mind. Okay, and I see that I have just very few minutes left, but I would like to just say a few words about how to tie this in with label information. And so here the idea is that we use the geometric information that we can incorporate in the graph Laplacian in addition to label information, and then propagate those labels to the other unlabeled points. And again, let's just look at two labels now, so binary classification, and therefore we can just pick +1, -1 to make our life easy. And we are not here in the supervised regime, so the number of labels is much smaller than the number of data points. And in the previous talk, Matthias Erhals was mentioning how to use machine learning techniques for solving inverse problems. So here actually you can make sense of this clustering algorithm or classification algorithm as an inverse problem, on the other hand. So you can write this, let's say you assume that your label y is generated by taking the sign of some ground truth function that you don't know, that lives on your labels, and also that has been corrupted by noise. And here we take a very general distribution of the noise. So this psi gamma can be quite general. So of course this is ill-posed, but in the end you don't need to find exactly this u dagger. You just need to find some function such that the sign of u dagger is equal to the sign of that function as the noise level decreases to 0. And so you can do that by formulating a probit optimization problem. And so this looks a bit like maybe the optimization problems that people use in image processing. So you have a data misfit term, which I'm not going to specify now here, but it's simply some function that forces the sign of u to be equal to y on the labeled points that we're given. And then you have just a regularization term. So, classical approach would be just to use Tikhonov regularization. But here we can actually package the geometric information from the data into this regularizer. And so I could have just put the graph Laplacian here. So L, here's just a graph Laplacian. You see that we have this complicated expression with the tau and the beta. So the reason for that is so that we can make sense of this formulation now as a Bayesian inverse problem. And if you do that, so if you shift this graph Laplacian, then you make it invertible, since then you're taking out the kernel basically. And so then you can make sense of this as the inverse of some covariance matrix, which is what you see here. So then you can think of this as basically finding the maximum of a posterior distribution given by the inverse problem that I showed you on the previous slide. So there's a really nice sort of structural form behind this. And then you can show that this minimizer exists and is unique. That's not too difficult, but very important that you have asymptotic consistency. So that actually in the limit as the noise goes to 0, it does recover the sign of the ground truth. And let me just finish with this last thought. So this is some recent work that we did on these sort of discrete semi-supervised learning algorithms, making use of the geometric information in graph Laplacians. But most of these notions also have continuum analogs, and something that is, an open problem on the table is how can we leverage these continuum analogs for algorithm design and also for analysis of algorithms. So, instead of working with the points, you're just working with the density. Instead of with a ground truth that lives on the nodes, you have a ground truth that lives on the complete domain where your data can be. And then you have some information on your observed labels, which you assume to have been generated by this kind of inverse problem formulation, which is just a continuum version of what I showed you before on the graph. And now to determine what this classifier is, you're actually learning a function by minimizing over a function space. And so here, this data misfit can be formulated exactly in the same way. And instead of having now the graph Laplacian, you're using this weighted elliptic operator as that you obtain in the continuum limits. And so this is actually still ongoing work that we're looking at the properties of these algorithms, parameter choices, consistency, and so on. And then, of course, how they perform on actual application settings. In terms of generalizations, we just by looking at different numerical examples and different test data, we believe that what we showed for a very specific rho epsilon and for only 2 clusters actually also generalizes to more than 2 clusters, and not only with tighter bounds than what we were able to prove theoretically. So these are the behaviors that we're conjecturing exist. And so what that means is that you actually want your Q to be always less or equal to P plus R in the normalizations that you're choosing in applications, because that will allow you to always have a uniform spectral gap, and therefore that your spectral gap does not depend on the size of how far away you are from a perfectly clustered piece. Okay, and with this, since I don't want to go too much over time, I will stop here. And yeah, thank you very much also for such a great conference. I really learned a lot from all the other talks.
Great. Yeah, thanks, Franca. Thanks, Franca, for your talk and also for answering the questions. Very nice work. Unless there's a very urgent other question at this moment, and I would say we stop, and that's yeah, that then ends the workshop. And we should definitely thank the organizers of this workshop for putting the program together. I'm not sure whether all of them are here, so that's Francis Bach, Gita Coutinho, Lars Rusotto, and also Peter Bartlett. So thank you very much for organizing this event. It was great. Good, and that ends this session. Thank you for attending.
Thanks, Johannes. I actually just wanted to add a few thank yous. Big thank you to the INI, of course, Gemma and everybody else for all their work in organizing things, and thanks to the session chairs and moderators, and to Carola for organizing all those in-person moderators, and a big thank you to all the speakers. It's been a great program. Thanks, everyone.